Hello viewers, welcome to the channel Amazing Civil Engineering Studies. Time to enter the world of civil engineering. Here we will learn about different concepts related to civil engineering. Please subscribe to the channel and press the bell icon for more new updates. In today's video we are going to discuss about structural engineering. Constructing shear and moment diagram using shear moment equation. We have already discussed about shear and moment and how to represent them using algebraic equation. Now, here we will discuss about graphical representation of shear and moment. Using these diagrams, we accurately and quickly determine wherein the beam shear and bending stresses are maximum or minimum, and how stresses vary across the beam, an ability that plays an important role in structural design. Before starting drawing of bending and shear diagram, let us establish a sign convention. In this diagram, note that left region of the shear diagram is labeled positive and diagram's right region is labeled negative. What exactly it is positive or negative shear means, that is what the sign conventions clarifies. Consider a simple beam carrying uniformly distributed load. If we cut the beam at point C, we need to show the internal shear force and bending moment at the cut point. Shear force has to be shown as a pair of vertical forces acting in opposite direction. So it can be drawn like this. First, in first scenario the shear force tends to rotate the beam segment in the clockwise direction. See diagrams. In second scenario, the shear force tends to rotate the beam segment in the counterclockwise direction. See diagrams. By convention, if the shear force direction tends to cause a clockwise rotation is considered positive. Hence, this is oppositive shear. If the shear force tends to cause a counterclockwise rotation we call it negative shear. Hence this is negative shear. Similarly, when we cut the beam, the internal bending moment is drawn as shown in below scenarios. In the first scenario, the bending moment tends to cause a concave up deformation in the beam like this. Oppositive moment tends to cause a concave up bending in the beam. Therefore, this is considered as positive moment. In the second scenario, the bending moment tends to cause a concave down deformation in the beam like this. Oppositive moment tends to cause a concave down bending in the beam. Therefore, this is considered as positive moment. Now, on to drawing shear force and bending moment. One way to draw the diagram is to graph their corresponding equation. For example, for this beam, formulating shear and moment equations. Let us assume they have been derived already in previous videos, links in description. V x equals 375 minus 100x Newton. 0 equals x equals 5. Equation 1. V x equals minus 125 Newton. 5 equals x equals 10. Equation 2. 375x minus 50x 2 Newton meter. 0 equals x equals 5. Equation 3. M x equals 1250 minus 125x Newton meter. 5 equals x equals 10. Equation 4. Now, we want to graph them for shear. We have two equation for left segment of beam. Where z between 0a and d5. Shear equals to 375 100x. This represents a line segment. See equation 1. To draw this we need 2 points. Say, the segment end points, so we evaluates the equation at x equals 0 and x equals 5. At x equals 0, V equals 375 Newton, at x equals 5, V equals dash, minus 125 Newton. First, locate the point on the coordinate system, then connect them with a straight line. Note that the line crosses the x-axis between 0 and 5, making the left part diagram positive and right part diagram negative. 4. Between 5a and d10 shear is given using the equation minus 125 Newton. Since here shear is not really a function of x, it remains constant throughout the segment. So, now shear diagram is completed for the beam. See above figure. We can graph the bending moment equation in a similar manner. For the first segment, where z is between 0a and d5, the moment equation is quadratic. Therefore, 375x minus 50x 2 Newton meter. 0 equals x equals 5. Equation 1. M x equals 1250 minus 125x Newton meter. 5 equals x equals 10. Equation 2. We need more than 2 points to graph it. Here, I use 3 points for generating the graph, the segment's endpoints and the point where moment is maximum. How? We determine the point of maximum. When moment is maximum, the slope of the equation is going to be 0. This means at the point of maximum the derivative of the moment vanishes, that is, since the moment equation is m x equals 375x 50x 2 Newton meter, then dm dx must be 0. Therefore, dm dx equals 375 100x equals 0. dm dx equals 375 100x equals 0. Solving the above equation for x, we get x equals 375/100 equals 3.75 meter, that is, moment is maximum at x equals 3.75 meter. Now, we have 3 points for graphing the moment equation at x equals 0, x equals 5 and x equals 3.75 meters. Solving the equation, m x equals 375 x 50 x 2 Newton meter, at x equals 0 m x equals 375, 0, minus 50, 0, 2 equals 0. So, at x equals 0, m equals 0. At x equals 3.75 meter. Solving the equation, m x equals 375 x 50 x 2 Newton meter, at x equals 3.75 m x equals 375, 3.75, minus 50, 3.75, 2 equals 0. m equals 703.125 Newton meter at x equals 5 meter. Solving the equation, m x equals 375 x 50 x 2 Newton meter, at x equals 3.75 m x equals 375, 5, minus 50, 5, 2 equals 0. m equals 625 Newton meter. The x-axis moment is considered positive in the region between 0a and d5. Moment in right segment of the beam, where x is between 5 and 10, is given by equation m equals 125125x. 5 equals x equals 10. This is a line equation. To graph it, let us evaluate the equation at its end points. At x equals 5, we get m equals 625 Newton meter. At x equals 10, we get m equals 0. So moment changes linearly from 625 to 0 in this segment. See the diagram for bending moment from x equals 5 to 10. So, complete shear force and bending moment diagram of the beam. See below. Thank you for watching. For now, please subscribe, like, share and do not forget to press bell icon.